Whenever we're looking for functional groups in organic chemistry, we're looking for anything that is not a carbon-carbon single bond or a carbon-hydrogen bond. Everything else is considered a functional group. So you would think there would be an awful lot of them, but because of carbon's really curious chemistry, there can be long stretches without functional groups. So when we start with A, immediately we recognize on the left we have this sp2 hybridized carbon, and it is double bonded to an oxygen, and on one side we have a hydrogen and on the other side we have a carbon. This is called a terminal functional group, and this specifically is an aldehyde. So it's always at the end of a molecule. If we move over to the right, then we come up with this oxygen, but that's not just our functional group. Because it is next door to a carbonyl carbon is an sp2 hybridized carbon that is double bonded to an oxygen, then we look at that sp2 hybridized carbon and we need to look to either side. So on the one side we have an oxygen and on the other side we have a carbon. This is called an ester. If we keep walking down this chain, then we come to this double bond. Remember, a carbon-carbon single bond is not a functional group, but a carbon-carbon double bond is. And this is an alkene with an E, alkene. So keep coming down that parent chain, and you come to a substituent that is a single bonded oxygen hanging off of the chain, and it's an OH group. So this is an alcohol. When it is charged, it is called a hydroxide. When it is covalently bonded in organic chemistry, the prefix would be hydroxy, or if we're looking at it as a suffix, we look at it as an alcohol. So we keep coming down that parent chain and we come to another sp2 hybridized carbon. That sp2 hybridized carbon is double bonded to an oxygen, and on both sides of the sp2 hybridized carbon, we have other carbons. So this is called a ketone. For B, we start on the left and we come down that parent chain. We come to an sp2 hybridized carbon that is double bonded to an oxygen. And on both sides of that sp2 hybridized carbon, we have other carbons. This is a ketone. Come down the chain and we have a substituent that has an oxygen single bonded to it. But on the other side of that oxygen is another carbon. So fundamentally, we would call this an ether, but I want to point out this is a special ether. So I do want to call it an ether because that is what it is. But this is a special ether. We would call this, as a substituent, we would call this methoxy. The meth for the methyl group here, the oxy for the oxygen. So this is methoxy. Similarly, if we had a substituent, and we have this long chain, right? And you have a substituent, and then you have an ethyl group on that oxygen, this would be called ethoxy. Okay, see how those are named. So then we walk down the parent chain again and we come to another sp2 hybridized carbon. This sp2 hybridized carbon, double bonded to an oxygen, on one side has a carbon, but on the other side we have a nitrogen. So that nitrogen is part of this functional group. And this is called an amide, A-M-I-D-E, amide. Sometimes you might hear it called amide. And look, here is an ether. Fundamentally, this is an ether, but this is that other special case that I pointed out. So this was called, when you go to name this is called ethoxy. And here, this is an alkyne, A-L-K-Y-N-E. Now, I also want to point out, because we have these two pi bonds create a linear geometry. We have carbons at every end and bend, so there's a CH3 here, but there is a carbon here, there's a carbon here, and then there's a carbon here. This carbon has two hydrogens. This carbon has none. Neither does this carbon, because there are 4 bonds showing. So I want to make sure that everyone understands how many carbons are involved here. This is an alkyne. For C, this is an ether. This is an oxygen, single bonded to a carbon on the other side. This is also an ether, but this is a special case ether. This is called an epoxide. And in Organic 1, we look at epoxides in Module 6. Now we keep walking down the parent chain. We come to another oxygen, but this time this oxygen is bonded to an sp2 hybridized carbon. So this is called an ester. Keep coming down the chain. We have an alkene. That's the double bond. Then we have another sp2 carbon. This is called a ketone. And it's called a ketone because both sides of the sp2 carbon have carbons attached to them. And then we have this. Now, this is a shorthand representation. So we have this molecule. Yeah. And then it says CHO. What does that mean? Well, let's decipher this a little bit. Whenever you have a carbon, it's going to make 4 bonds. We have 1 bond showing, and that bond showing is bonded to the rest of the molecule. So I'm just going to call this the rest of everything R. And I have an H and an O. So that carbon has an H. That's terrific. So it must be bonded, double bonded to the O in order to satisfy its octet. This is called an aldehyde. Aldehyde is a terminal functional group, and when it's written out in condensed form, it's written CHO. If we wrote it COH, that means the oxygen is bonded to the carbon, and that would be an alcohol. So it's important to note the difference there. This is an aldehyde, CHO. For D, now D looks a little bit strange because we do have this complex ring structure. So how are we going to pick this apart? Well, we're going to start with our sp2 bonded or our sp2 hybridized carbon that is bonded on one side to an oxygen. The other side gets a carbon. So this is called an ester. Here we have our alkene with an E showing the double bond. This is an alcohol. And this is an ether. Remember, when we go to name it, this ether we would actually call a substituent, and this would be methoxy. In E, we have an alcohol here. We have our sp2 hybridized carbon, but it has 2 carbons bonded to it, so we would call this ketone. And here, what do we do with this? CO2CH3. Well, this is the condensed formula for, let's see if I draw this out here. We have a double bonded O, we have a single bonded O, and then we have this CH3. So this is an ester. For F, we have this NO2 group. This is called a nitro. Here we have chloro, or you could call it a halogen. Either way is fine with me. And then what do we do with this? Well, this, with the oxygen in parentheses, shows us that it's a double bond. It's another way to show it, and this is a ketone. And I know it's a double bond, and I know it's not an ether because there are no hydrogens listed, and this is a condensed formula. So I know that the oxygen must be double bonded in order to satisfy the octet of what's shown with this carbon. For G, I have an sp2 hybridized carbon here. This is a ketone. Here is an amine, A-M-I-N-E, amine, and that's the nitrogen with anything that's around it. Here's one of those special case ethers called the epoxide. And here is a carboxylic acid. On H, I'm not even sure where to begin. So here's alkene. Here's an alcohol. The OH group is called an alcohol. Here's a chlorine or a chloro group. You could call it a halogen. Here's a ketone. And here is another one of those shorthand versions or condensed formula versions where you have to realize what the Lewis structure would look like. So this would be a carbon double bonded to an oxygen and then single bonded to an OH. This is a carboxylic acid. Here's another shorthand version or condensed formula, but this time the H's are on the left. So what's going on? Well, it's showing you the bond order here, and this is an ether. The oxygen wants to make 2 bonds. One is to the ring, and the other is to this carbon. This carbon has 2 H's, and then is bonded to this carbon, which has 3 H's. So you see how that works out. Then we have this benzene ring, and then this group here, this is called an amide, A-M-I-D-E, sometimes pronounced amide.